Hello students, now we are going to study about the nuclear force. So inside the nucleus we know there are nucleons, that means protons and neutrons. So if we have a nucleus, we have some neutrons and protons inside it like this. Neutrons are neutral particle, there is no charge on neutrons, while protons are positively charged particles. So if we talk about electrostatic force of attraction or repulsion, proton right, proton are similar charge, positive, they show repulsion, while proton neutron and neutron show no such kind of force, no electrostatic force of repulsion, because neutrons are neutral. But since nucleus is binded together, or there are nucleons which are attracted to each other, which are bind to a closed space, as we see in the density of the nucleus, so there must be some attractive force which is holding all these nucleons together, right? There is a need of, or there is a existence of some strong attractive force which is holding these nucleons together, and that strong attractive force which is interacting between the nucleons, we call that force as nuclear force. So nuclear force is the strong attractive force or strong attractive interaction acting between the nucleons. Nuclear force is the strong attractive interaction acting between the nucleons, and this is responsible for binding the protons and neutrons together inside a tiny space of that nucleus of the order of 10 to the power minus 15 meter. So this is responsible for binding protons and neutrons together inside a tiny nucleus. Now there are certain properties of these strong nuclear forces. Let's talk about their properties. The first property that nuclear force possesses is these are the strongest interaction present, as we have mentioned in the definition also. So it is one of the property also here that nuclear interaction or nuclear forces are strongest interaction. So nuclear force is the strongest interaction known in the nature, as they are holding nucleons together in spite of the electrostatic repulsion present between those protons, right? Proton are showing electrostatic repulsion. In spite of that, nuclear forces are binding them together in a small space. That's why these are the strongest interaction known in the nature. And if we compare them with other forces, with gravitational and electrostatic forces, then we get the ratio of this gravitational force compared to electrostatic force compared to nuclear force, give us the relation 1 is to 10 to the power 36 is to 10 to the power 38. So these are the strongest known interaction in the nature. The next property that we have is the short range forces. These nuclear forces are short range forces. Unlike gravitational and electrostatic forces, their range is very small, like they are only effective up to a distance of about 2 to 3 Fermi that form a nucleon. So that's why their range is very short, and it is approximately 2 to 3 Fermi. We can experience the effect of short range forces up to 2 to 3 Fermi. Next property is that these forces are charge independent. These forces are charge independent, as we are getting the force between neutron proton, and neutron. That's why we call it as charge independent force. Next property that these nuclear forces possess is saturation effect, and by saturation effect we mean that these nuclear forces show saturation effect means a nucleon interacts only with its neighboring nucleon, right? Hence, by saturation effect, we mean that a nucleon interacts only with its neighboring nucleon. That is called saturation effect. These nuclear forces also show spin dependent character. That means their strength depends upon the spin of the nucleons on which they are acting. Means the nuclear force between two nucleons having parallel spin is stronger in comparison to the nuclear force between those two nucleons which have anti-parallel spin. So spin dependent character means if there are nucleons with parallel spin, the nuclear force acting between them is stronger. If the spin is anti-parallel, the nuclear force acting between them is comparatively weak. Next property that these nuclear forces possess is these are non-central. So the nuclear forces are non-central. The nuclear force between two nucleons doesn't act along the line joining their centers. This is the sixth property. The next one is these are exchange forces and there is a continuous exchange of a particle called meson's hair. So mesons are the particle that get exchanged between the two particles in which this nuclear force is acting. So the graph here shows the potential energy of a pair of nucleons as a function of their separation. So we are plotting the potential energy as a function of r, where r is the separation between two nucleons and r naught is the minimum potential energy distance. That means r naught is the distance at which potential energy is minimum and it is equal to 0.8 Fermi. Now the potential energy, if the potential energy has positive value, it shows repulsion between them, and if the potential energy shows negative value, it shows attraction. So if r is less than r naught, that is 0.8 Fermi, the potential energy increases rapidly with decreasing r. So if we see the points that is less than r naught, in this case the potential energy increases rapidly. This is the increase in potential energy, increases rapidly with decreasing r, and it shows strong repulsive forces, right? If r is less than r naught, potential energy increases rapidly and it shows this positive potential energy shows repulsion between nucleons or the repulsive nuclear force. It is representing repulsive nuclear force. Now after that, if r is greater than r naught, right, if the case is in which r is greater than r naught, in that case the potential energy gradually decreases to 0. If r is greater than r naught, potential energy is gradually decreases to 0 with increasing value of r, and it indicates the attractive nuclear force, and this attraction is a maximum at r is equal to r naught. This is the maximum attraction point at which the value of attraction is maximum, because at this point the potential energy is at most negative point. So if r is greater than r naught, potential energy gradually becoming 0 and maximum potential energy is at point r is equal to r naught. Actually we have to write maximum potential energy in negative. This is a negative maximum potential energy which is showing attraction. So this basically shows the maximum attractive nuclear force. This is the point at r is equal to r naught, is the point where the potential energy is most negative, and there that's why at that point the attractive force is maximum. The next point is, if R reaches to approx 4 Fermi, right? If it reaches here some point at about 4 Fermi, at that point the nuclear force become 0. If R approaches to 4 Fermi, the nuclear force at that point become 0. It indicates that nuclear force is a short range force, means it only act up to this point. After that there will be the 0 value of nuclear forces, no effect of nuclear force can be experienced. So nuclear forces are short range forces. And the negative sign of potential energy here in the graph signifies the attractive nature of nuclear force. So this is the attractive nature of nuclear forces. For the distance less than r0, they show repulsive nature, but for the points more than r0, at the distance greater than r0, the nuclear forces are attractive up to 4 Fermi, and after 4 Fermi there will be no effect of nuclear forces, as these are short range forces. So that's are the properties of nuclear force. That's all for the video. For further videos, stay tuned and keep studying. Thank you.